Okay, so we'll try to touch upon a very interesting technology, which is OFDM. So before going to OFDM, I'll just give you a brief idea. Like OFDM started, like cellular technologies started using OFDM in 4G. Before 4G, there was CDMA that people used to use. And then before that, DMA, TDMA. But in 3G, we had CDMA. In 4G, we had OFDM. And then 5G also, we are using OFDM also. So OFDM is used in both 4G as well as 5G. And 6G also, we don't know whether it will be OFDM or some other multi-carrier technology, maybe filter bank multi-carrier or something like that. Something called OTFS is also there. And so everyone knows, like most of you guys, if you have interest in this wireless system, OFDM is something most popular technology, and wherever you go, people will are working on that, and most of the questions, interview questions, always come from OFDM only. If you are applying for any job somewhere, be it a PhD interview or some job interview, you'll have that always. So one important thing is like we just go and look into the basic of OFDM. This is I've just taken this diagram from the internet. So this is a basic block diagram of OFDM, where we take the signal constellation mapping, we do the serial to parallel. We take the IFT, then we do the parallel to serial conversion. We insert CP. We do digital to analog conversion. Okay, this is a simple transmitter that we have, and similarly to receiver, we are doing the reverse operation. We move CP, signal to parallel, serial to parallel, FFT, and parallel to serial. So we can see at the transmitter, like most important concern here is about inserting CP to avoid the inter-symbol interference, and that we are removing that. The rest part is very trivial, simple. If we want to go, if we just implement an MATLAB this OFDM transmitter, it's not that much difficult to implement. But now when we bring the, now I'm trying to bring the standard also. When I say standard, like cellular standard, like that is been developed by the international body, 3GPP, Third Generation Partnership Project. Okay, under the umbrella of 3GPP, on standard is being developed. Fine. In that, if you see, they're given certain, there are multiple block diagrams that we have to implement. Before the OFDM, if I would say, like, suppose a user is transmitting a data, or a base station is transmitting a data, maybe in uplink or downlink. When user is transmitting to base station, we call it uplink, and when base station transmit to user, we call it downlink. Okay, when the user is transmitting data, it's not like directly it is transmitted to the over the air. So many processing happens before it is transmitted over the air. For example, suppose for example I'm transmitting a data. Okay, so I have a data to transmit. So first of all, it may go through the block diagram, like outside the practical modules, like cyclic redundancy check to ensure that the receiver, when the signal is received, it is received without an error. To check and detect, to detect and correct error, we use cyclic redundancy code in the transmitter. Then we use something called, so many things, whether you guys are knowing about that or not. For example, something called rate matching, scrambling, interleaving. So many different processes happens at the transmitter. Before it is actually transmitted, it is passed to the OFDM. Okay, so before this point, before a point, so many processing is happening before. Coding happens, turbo coding, LDPC. Depending on 4G, there was LDPC, turbo coding used to happen. In 5G, we have LDPC coding. And there are multiple channels also, data channel. So I can give you a brief idea about that before moving here, just so that you'll appreciate what exactly happens. That is in itself, it is very complicated. Let's see here. Okay, if you see, if suppose for example, in any wireless communication, the standard when they develop, they've divided into something called control channel, where all the control information is passed. There's a data channel. Okay, control channel, they call it, and data channel. Okay, Here all the control informations are passed. Here all the data, actual data is passed. Control information, so many control, whether okay, because just think practically, okay. When suppose user is entering into a base station coverage, a cell, we call it the cell, right? So many processing will happen. When the user is coming, its information need to be shared to the base station. Base station will accept it. Okay, he or she can be a part of the network and all those things. So many things happen. Although it happens in a microsecond or millisecond of time, but all those things happens. Okay, so there are two, we say, physical uplink control channel. Okay, so when the user, when the transmission is happening from user to base station, there is something called physical downlink control channel. Okay, now this is self-contained. This is nothing but PUCCH. This is PDCCH, physical downlink. So if you read a standard, you'll get this kind of terminology in control channel. Similar data channel counterpart, there is something called physical uplink shared channel. It's called PUSCH. Similarly, we have physical downlink shared channel. This is called PDSCH. These are the four important. There are others also, but these are the four important channels, four important chains that is there that okay that helps the data to be transmitted either in uplink, the control channel in uplink and downlink, only the data in uplink and downlink. These are the four terminologies that is being used. And then when we transmitting, like I take an example. For example, we have a data. We take the data, we pass it to CRC. Okay, just randomly I'm saying giving. I'm not giving you the complete picture. Okay, we pass it to CRC. We do some kind of segmentation. Okay, we do some kind of coding. We do interleaving. So I'm giving you just a brief idea what all things we do. Scrambling. Each of these block have their own advantage. Why to do? There's a reason behind that. We're not going to detail. Okay, and we do modulation. Then comes the where we use the OFDM to transmit. Okay, and then this transmit over the air. Fine. So this is what happens in the. Well, I'm just giving a roughly. This is not the correct exact one, but I'm just giving so many processing happens before the information is transmitted over the air. So this part, as of now, I'll just take it. I've taken it from the this part till here, from here to here. We'll assume that this processing is done. After that, we'll take this what is in OFDM. Okay, so I'll be focused more on the part where the OFDM starts. Fine. But I'll just give you a brief idea. Suppose someone is interested. There's a MATLAB code available, which can be used by anyone. MATLAB has written as an open source. Anyone can use it. So this is that code. If you see, okay, PDSCH underscore. If you write it, you'll get this. Okay. You can go in the internet, go to the internet, write the PDSCH NR PDSCH throughput MATLAB. You'll get a code and you can run it. I'll just give you a brief idea, very brief idea. I was talking about this all channel, right? Physical downlink shared channel, physical uplink shared channel. So all these things you can see the same kind of thing. So if I was saying you, I'll just give you a brief idea because it is very difficult without knowing the theory of it to directly understand the coding. And with the shortage of time, I'll try to give you more as much detail I can give you. But it would help me also if you guys let me know if you guys have any specific thing in mind that you want to understand, okay, or any doubt you are getting. So if you see this, all things are fine. I think So you just go through it. I'm just telling you what all this code is all about. This the existing MATLAB code that you can use it straight away if you understand it. Okay, so this will consist of so many things like number of antennas, how many transmitter antennas are there, how many receive antennas are there, what is the modulation technique we are using, QPSK or 16 QAM, what is the code rate. I was asking, telling them there is some coding, turbo coding or LDPC in 5G. So this is the coding rate that we are using. So all the things that this will cover. So many parameters are there. It's not easy. So now when I'm talking, so all this processing is happening, you can see. And my focus is directly on OFDM, right? For today's talk, we're focusing on OFDM. So before this, so many things have already happened. Now we are focusing on OFDM. Now coming back to the slide. I'll try to make a slide so that it is clear, like you will be able to get the idea. Okay. So we have the, for example, like I said, we want to do the OFDM transmitter. Okay. So now we are focusing on OFDM transmitter. When we do OFDM transmitter, what are information we have? Okay. I said before OFDM, I'm taking the data. So this data is coming from there. This is the before OFDM thing. All the blocks are there, all the blocks are done. So I'm taking this data from somewhere. Like I've generated this data, I'm putting it here for OFDM. So which is of size k by n by p. Okay, k is the number of subcarriers, how many subcarriers are there, and how many OFDM symbols we are transmitting per slot. Okay, this is about that. So before going to that, also I'll give you a definition of, if you guys don't know about that. What is slot, what is in 5G and all those things. Let me brief you also about that. So in 5, there's some few terminologies that are very important. One thing is like numerology, subcarrier spacing. These all things will come across today. Subcarrier spacing, slot, frame. Okay, this kind of terminologies we are going to see today. So in the MATLAB, when we do the OFDM coding, this all things will be coming. Numerology and subcarrier spacing are connected. So there are many terms numerology 0, 1, 2, 3, 4. Okay. With the numerology mu, if I denote it as mu, we have subcarrier spacing if I'm denoting it by delta S. The subcarrier spacing is like this. Is given by 2 to the power mu into 15 kilohertz. Okay, which will come out to be here 2.0. This is 15 kilohertz. Okay, with numerology 1, if I'm using, I get 2 to the power 1 into 15. So this is nothing but 2 to the power mu into 15 kilohertz. I'll get this as 30 kilohertz. Now you would have understood this is 60 kilohertz of subcarrier spacing and 120 kilohertz and maximum 240 kilohertz of subcarrier spacing. Okay, this is the sub, and we know in the OFDM subcarrier spacing is very important because of the, if you guys have know about OFDM, they all are placed like this, right? And this is the subcarrier spacing that we want. Huh? Subcarrier spacing is very important, and the subcarrier spacing is increasing. And see when the numerology is increasing. So which numerology to choose and all the things, so that is already been decided before. We are not going to that detail, but we should know if we are choosing numerology 1 that we are choosing for today's talk, will have a subcarrier spacing of 30 kilohertz. Okay, so this is done. This two terminology that will be coming in. Another thing is slot. We say in one OFDM, 1 millisecond, how many number of, like for example, 1 millisecond frame, how many number of OFDM symbols are being transmitted. Okay, it depends on the how many what is the subcarrier spacing. Depending on the subcarrier spacing, if suppose we have 1 millisecond of frame with subcarrier spacing of 0, we'll have suppose X number of OFDM symbol transmitted with subcarrier spacing of 30 kilohertz with numerology 1 will be transmitting 2x number of OFDM symbols. Because what is happening when we are increasing the subcarrier spacing, increasing frequency, in time we are requiring 0.5 millisecond. It is reducing 0.25 millisecond. We are making multiple frames. You get these ideas. I think you guys would not be knowing about standard and all those things, but I'm just trying to give you very basic information. Maybe when we go through the MATLAB code, you may understand. But just think that this is like, for example, 14 OFDM symbols are there in one slot. 14 OFDM in one slot. This you need to remember. Okay, 14 OFDM in one slot. And let us go to the slide. Maybe you'll get an idea. I'm just trying to give you some picture. See, you can see here what we have. This carrier. You see. Okay. The carrier, if you see, carrier is the information, basic information that everyone will have that is passed through the control channel. So what we have, subcarrier spacing of 30 kilohertz, like I said, right? 30 kilohertz we have. This is the size of the grid in OFDM. In the 5G, we have the grid, N cross K grid. This is the N cross K grid. So complete subcarrier now we are using is 51 subcarrier. K sub, just remember, there are few terminologies that you'll get. K is number of subcarriers. N is the number of OFDM slot symbols per slot. P is the number of transmitting antenna. Suppose we are using 8 transmit antenna, so P will be 8. N is the number of OFDM symbols per slot, which is I said 14 symbols per slot. OFDM symbol per slot is 14. Okay. And then this are thing you can ignore for now. Just for your case, you should remember what is the symbol per slot, which is 14. What is the subcarrier spacing, which is 30. The size of the grid, I'll explain you in short time. This is size of the grid in y-axis. Okay, this you'll understand. So just for now, you should understand from this slide what is the symbols per slot, which is 14. What is the subcarrier spacing we are going to use. Okay. Now this is the input. This is the input signal for which we need to take the OFDM, or we need to do a modulation based on OFDM. And this is the carrier information that everyone has based on the proper to control channel or something. We have already passed this information. Now when we move ahead, and this you can see, this is just, you can obtain through formula, as like I said, 2 to the power mu into 15. Right, I gave you in the screen. And this is something called cyclic prefix we are taking to be normal, that I'll explain in further slides. And this is something I said 14 for normal cyclic prefix, we are using cyclic prefix normal. And this all things are fine. I think you'll understand. Now let us move ahead and I'll tell you how the things are calculated. Okay. So when we have, like I said, if subcarrier spacing is given, like subcarrier spacing was given as 30. From subcarrier spacing, I can always calculate mu. It is 1-to-1 mapping, right? If I know mu, I can calculate subcarrier spacing. If I know subcarrier spacing, I can calculate mu. So we can calculate it, right? Now, important part is here. You remember, I said we have given size of grid is given, right? Size of grid is what? 51. From the size of grid, we calculate how many number of subcarriers are there. Once again, I'll repeat, from the size of grid, this grid, we calculate the number of subcarriers. And how it is calculated is just by multiplying the size of grid by 12. Okay, the size of grid is 51. We are multiplying it by 12, and therefore we are getting K as total number of subcarriers as 612, 51 into 12. And all those things what I'm talking about is coming from the standard. Okay, that's why I've referred also 38.211. In the particular section, they have given this formula. So in 38.211 standard, this is a document number. The multiple documents in 5G. So this is one of the documents that we have to follow where they have talked about OFDM or related things. In 38.211, section 4.4.4.1, when we go, you'll get this formula. You can take a screenshot of this and you can go back Go there, just write in Google TS 38.211 3GPP 5D document. You'll get this. In the section, you'll get this. Okay. Once again, we have calculated the numerology based on the subcarrier spacing, and we have calculated the number of subcarriers. This will be used later. That's what I'm saying. Number of subcarriers based on the size of the resource grid, and each resource grid can have 12 number of subcarriers. Therefore, overall subcarriers that we have is 51 into 12, which is 612. Then, now further moving ahead. Okay, further moving ahead. I think this is not important. Yeah, here we'll see. Like I said earlier, okay, CP is very important, right? Cyclic prefix is very, very important. So we need to see how can we use cyclic prefix, how to use cyclic prefix, how much cyclic prefix length should be there. All those things standard tells us. Okay, standard is there. It tells us based on the number of the FFT, NFFT, size of the FFT. Based on the size of FFT, standard has given a table from where we can see, okay, what will be the size of the cyclic prefix. So for example, if we have a cyclic prefix like this, okay, for example, okay, I'll tell you, if the exact number of size of the FFT is 128, in that case, if the size of the FFT is FFT is 128, in that case, we'll use this CP to be this. And this one important point to see here is this part. The first one is 10, rest 6 is 9. Once again, 8th one is 10, rest 6 is 9. I said, right, total OFDM symbols are 14. So if you count this, this is 14. 1, 2, 3, you'll count this is 14. Now in 14 also, we are divided into two parts, 7, 7. Okay. And in this 7, 7, first one, they have allotted it 10, rest one is 9. Similarly, the 8th one, they have allotted 10 and then 9. Similarly, it is happening for 256 also. If you see, when we have the FFT size as 256, size of FFT is 256. If the first one is 20, rest is 18, and the 8th one. So first one and 8th one is 20, rest all is from 2nd to 7, and from 9 to 14 is 18. Similarly, you can see that. Okay, it's coming from standard, so we'll not go into the details of that. There is also a reason for that, but for now, we will not go into that. So you can see one more thing. All the FFT size are multiple of 128, right? You see, all the FFT size are multiple, just into 2 into 2 into 2 is 7. The multiple of 128. Okay, if you see, and in this today's talk, we are considering the FFT size of 12024. And K we have already calculated 612. So these are the two important, for any OFDM system, these are two important things. What is the FFT size we are choosing, and what is the number of subcarriers we have. So FFT size is 1024 that we are selecting, and K we have calculated based on the size of resource grid as 612. Resource grid into 12, 51 into 12, we got 612. Now we need to calculate what is the sampling rate. Okay, what is the OFDM sampling rate? And this is given by what is the subcarrier spacing we have and the size of the NFFT. So this is nothing but N size into subcarrier spacing, N into delta F. If you guys should have remember, this is nothing but N into delta F. You can see this kind of formula, N into delta F. N is what? The size of the FFT, here you can see, and delta is the subcarrier spacing. If you just multiply this, okay, you'll get the sampling rate, because this formula is like sampling rate is 1 by Tc. You just remember, sampling rate is nothing but number of size of the FFT into the subcarrier spacing, and therefore after substituting we got this number 3072410. This is the sampling rate that we are getting, and sampling rate is important whenever you do a practical kind of function, because you need to see how many samples per second you are getting. Okay. Sampling rate is nothing but samples per second. So we have got this information based on the subcarrier spacing and as well as number of the size of the FFT. And why we have multiplied 1 into 10.3? Because I said this is 30 kilohertz. So 30 kilo, this is K hertz into the N. Right, now further moving, if you like one thing I was telling you, this is a subcarrier spacing mu. Based on the subcarrier spacing, we have different number of slots and all those things. So I said, right, the number of symbols per slot is fixed. Number of symbols per slot is 14. Correct? Irrespective of the numerology, if you see, irrespective of the numerology, number of symbols per slot is fixed to 14. But now, how many slots are there in per frame? Now that we are going to see. Okay. So how? See, once again, I'll repeat. This is number of symbols per slot. This is 14 fixed. But how many slots are there per frame? It depends on the numerology. Okay, and this is moving from 10, 20, 40, 80, 60. Because like I said, as we are increasing the subcarrier spacing here, the timing required is less. Now if suppose for example we have a 10 millisecond frame size is 10 millisecond. Okay, frame size is 10 millisecond, and one sub frame size is 1 millisecond, and one subframe, like so for example 10 frame consists of one frame consists of 10 subframes, and each subframe is of 1 millisecond. So this is 10 millisecond, right? So we have 10 subframes. We assume like that. So in the next one we'll have 20, 40, 80, 160. So we are, because the timing required is reducing to the by half every time, half. So we are able to support more and more subframes, more and more frames, and therefore more and more subframes. You can see more 1, 2, 4, 8, 16, 10, 20, 40, 50. This is, you can go back and see. The just relation is as the number of subcarrier, as the subcarrier spacing is increasing, the timing is reducing, and because the timing required for one frame is reducing, we are able to support more frames in the same time structure. In 10 milliseconds, we are able to support 10 frames, 10 slots per frame. Here we are able to support 20 slots per frame. Here we are able to support 40 slots per frame, and vice versa. And similarly, this is number of slots per subframe. Okay. Now, when we are moving ahead, now how many number of OFDM symbols per slot? And now there are two things, two cyclic prefix. Like I said in the earlier, if you see, there was cyclic prefix was mentioned in normal, right? Normal cyclic prefix. There's some, which was this normal cyclic. There's also something called extended cyclic prefix. There's an exception in the all the normal cyclic prefix, irrespective of what is the numerology, the number of slots were 14, right? You can see. But when we have extended cyclic prefix, in that case, for a special case of numerology 2, the number of slot is 12. Because it will happen if I'm saying extended cyclic prefix, I'm increasing the length of cyclic prefix. Extended cyclic prefix means now the cyclic prefix length is more. Now, since the cyclic prefix is extended, the number of OFDM symbols is reducing from 14 to 12. This you should remember. Okay. Now we are looking into the code for that. Now we are saying based on this section standard 4.3.2 section of TS 38.211 document, if we have extended cyclic prefix, if we have this, then we are saying length of this is number of slots. Okay, the number of symbols in one slot. L is, we are saying 12. This is 12, right? I'm just doing the coding based on this. We are doing 12. Otherwise, we are taking 14. Once again, I'll repeat. If the we are having extended cyclic prefix, if yes, then L is 12, else L is 14 from this table. Fine. Now what we are doing is we are moving and trying to find out what is the number of slots per subframe. This one. We can see one through right formula also. This number of slots per subframe is coming to be 2 power 0, 2 power 1, 2 power 2, right? If you see 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4. We're getting it. So we just calculate what are the number of slots per subframe. This is done. And then, like I said, this we have done it. Now, like I said, this is also this equation that I've shown in this thing is coming from this standard 38.211 section 5.3.1. It says to calculate. It asks us to calculate number of CP based on this formula. Okay. So now I'm first of all writing this factor that is 512, 144, and 144. So this factor for extended cyclic prefix is 512. So that I've written. Extended cyclic prefix, this formula NCP is 512, and for normal cyclic prefix it is 144. I've just written this code. After this, what we are going to do based on the subcarrier spacing, this will be reduced. If the subcarrier spacing we have chosen, if you remember, is 1, right? You can see mu is 1. Since mu is 1, what will happen? 144 divided by 2 will happen for this. So what will be? It will be 144 divided by 2 is 72 plus 16. If you guys, I told you, right, there was one table, this table. How we are getting this, we'll see now. How we are taking this 1024. Now we are seeing how we are getting this length. We are getting this length based on this formula. 80, 72 was there. Na? If we had 144 and kappa is 1. Okay, remember this kappa is 1 only. So 144 into 1 into 2 power minus 1 means it is 1 by 2. So 144 divided by 2 is 72. Here 72, here 72 plus 16 because kappa is 1. So what we are getting 72 plus 16 as 80, right? 80. So what we got is 80 and here what we are getting is 72. That's why for L equal to 0, we have 80. For L not equal to 0, we have 72. With an exception for L equal to 7 into 10.0 also. So what is 2.0? 2 power 1, sorry, here 1. Na? 2 power 1 is 2. This is 7 into 240 based on that. So we'll see that, like what I said, the same thing will apply. We'll do this coding here. This is what NCP was there. I've used that method. And finally, we are getting 72 here. And based on that, you'll see here, I'm getting finally, after doing all those things, I'm getting 88 here. Sorry, 72 plus, how much was there? 16 was there, no? Not 18, sorry. So 72 plus 16 gave me 88, right? If you see the formula, this was 72 plus 16. 72 plus 16 is 88. And that we are getting, you can see from it. I'm doing the same thing here, whatever I explained. So we had this 72, I applied all those things, and finally I got it. I've done the coding for that. I've got 88, 72, 72, 88, 72, 72, 72. Okay, because we saw that based on this formula, L equal to 0 will have 144 plus 16, means this, sorry, this will be 72 plus 16, 88 for L equal to 0, and then this is for all. And this is L equal to 7 into 2 for mu. Mu is what? 1. So L equal to 14 we are getting. So 0, then 14 we will get once again 88. Same thing we will see. We are getting in 0 and this is 0. And then in 14 we are getting 88. Based on that formula, I am now telling 0, then 40. Rest all here it is 72. I gave you one table where it was mentioning from 1 and 7, but it depends what is the mu there. Okay, that formula may have mu equal to 0, but now we are taking mu equal to 1. Because of mu equal to 1, this, if we took 7 into 2, we are getting. So 0th and 14th will be like that, not 0th and 7th. If mu is 0, for example, mu is 0, in 0th and 7th, we'll get slightly higher cyclic prefix name, and rest all will get lower cyclic. Right? That we can see from this also. We have got. Right? Rest all is fine. This, so I have told how 144 to 72 divided by 2 we have done. This 1024 divided by 2048. And then we got this all 72, and then I converted into 88, 72, 88, 72 based on the formula that was given there. This formula, right? This was the formula 88, and I hope this is clear. And here I'm calculating, one line is there where I'm calculating slots per frame was 2 because this was 2 power mu. 2 power mu is 2 into 14. So we are getting total 28. Therefore, I'm taking all the slots in one subframe. So this is the complete slots in one subframe, which is 28. Okay, any doubt till now? Any doubt till now?
No, sir.
Oh. Now when we are moving from here to next, now we have calculated what we have calculated till now based on the length of the FFT and the length number of subcarriers. We have calculated the size of the CP, length of the CP for each slot, and we see the size of the CP for each slot differs. It's not same for all. It's not like this 72 all. It is for the first and the 14th slot. It is different when compared to others. I would say 0 then 14. Now, when we are doing this, one more formula that is given in standard, it says this is a standard formula for OFDM. Okay, so we need to do this thing. Like you can see AKL. This see when you read the standard. It's very complicated. It will not say, okay, do this, do OFDM. It will give you a formula, say, okay, this is a formula that you need to implement. So as of now, when we do the coding, we need to take care of everything. Okay. So now if you see, this formula is there where we need to do it for j twice by this into it. This also is there, this part. Now I'm trying to implement this part. Okay, remember. So I'll calculate this NCP and T mu star. If you see, this NCP is nothing but the size of the, this is size of the CP. Okay, and this N mu is the size of the NFFT. So N mu is the size of the NFFT, N mu is the size of the CP line that we have calculated just now in the previous slide. Now what I'm doing is, this two we know, this we know. Now what I'm doing is, I'm just trying to place this thing. If you just see what I'm doing here, okay. What I'm doing is, this comes from what it does is, it takes the summation of all previous. What was the size of FFT 1024, right? I'm adding 1024 with the 88. If I add 1024 with 88, I get 1112. Once again, I'll repeat. I'm adding 1024 with 88, and I get 1112. So this is the first sum. Okay. Now, second one, what I'll do, I'll just add on this. This is the number of samples first. I'll add once again 1024 plus 72. Okay, this is 1024 plus 88 plus 1024 plus 72 will get this, plus 1024 plus 72 will get this, and so on. I've created this, and finally what I'll do is, I'll create dividing it in terms of slot. I'm saying the first I'll take sample from 0 to 1112. Then I'll take from this 1112 to 202220. So this is my slot multiple 1, 2, 3, 4, 5. So these are the samples that I'll be processing in each OFDM symbol. Okay, this is clear. Fine.
Yes, sir.
Now what I'm doing is, anyway we have calculated this SR. Based on that formula, I'm using this phase compensation. You see, there was e for j twice pi f naught t minus t1. I'm just calculating the phase right now. It for whatever phase was there, I have calculated. For j, this phase I have calculated and kept it with me. Okay, so this is done here, and this t will start, and this, and if you see, this was earlier in this was just, it was the index. This was the index we calculated. What is the number of? Now we need to calculate based on the sampling rate. This was the index. Now based on the sampling rate, we need to calculate number of samples t. So we have calculated NTS. If you guys remember, it is like t equal to NTS, right? If you remember from the digital, small t is equal to small n into capital TS, sampling rate. So this sampling, this is what sampling rate. That's why we have divided Fs. This is Fs. So 1 by Fs is equal to Ts. So this is n into Ts we are doing. So only n into Ts we are doing, and we are getting this. How many number of, and then we are calculating. Fine. Time. Now what we are, like, this is the one that I said, we are doing this through this formula, we are calculating this. Now further when we are moving, okay, so we are now trying based on those. So we have calculated what we have done till now. We are doing some initial processing. We are calculating what is the symbol phase based on the formula. We are calculating what is the CP length, what is the number of subcarriers, what is the length of IFT we are choosing. All those things we did till now. Now we are going to the actual modulation part. Okay, this was just initial processing, initial calculation that we are doing for modulation. So now we have this modulation, this function in the MATLAB, which does the modulation, or we modulate. Where this grid is nothing but the input. Like I said, 612 is the size of number of subcarriers, right? 612 we calculated, which was 51 into 12, which gave us 612. This is the number of OFDM per slot. And this is the number of transmit antennas that we have. That's why the size of the grid is complete 612 cross 14 to k cross n cross p that I wrote. Okay. Now, this is the info that we have calculated, all those things, FFT, subcarrier spacing, the 30 kHz sampling rate we calculated, right? Remember? And all those things are there in this part. Number of slot. Fine. So next we have From that, what we are calculating, from the grid, we are calculating back the number of slots. This is fine. I think this is, should not be a problem for you. And yeah, we calculated symbol phase, right? Now, based on a symbol phase, we are just doing multiplying whatever our input was, grid was there. This is our grid, right? Input x, for example, x into it for j into symbol phase. We are doing that because we have calculated symbol phase, but we never multiplied with the actual signal, right? Now here we are multiplying that. This function, what it does, it just multiplies this complete grid with the symbol phases that we have calculated. So this is, remember, this is e for plus j, and you will see in the rest, the receiver side will also do same thing, which will call mostly phase post compensation. It will be e for minus j kind of. Here it is e for plus j into phi. This is phase. There it will be minus j phi. So we'll here we are doing pre-compensation. There will do phase post compensation. Here it is phase pre-compensation. You remember the name here. Here it should be phase post compensation. Okay. And this is happening all based on the standard. We're not doing anything based on any just random thought that is coming into our mind. It is coming from the standard proper. Okay. Remember this we are doing now. It for j phi it was there. So j phi. Okay. Now what we are doing is, most important thing is, if you see, this complete thing is still not done. Okay. Now we are trying to calculate. Okay. Now we are trying to calculate the grid. Like we know from grid, we are, what I'm doing from grid, I'm just taking k back. We know. So from grid, if the grid is this, I'm just taking the k back. So k I'm getting 6, 5, and 12. Okay. Same thing I know what is the size of IFT and what is the size of k. Now, based on this is now going to very important concept that we are going to see here is, now what we are doing, I know my complete number of that is 1024, right? I have 1024 from NFFT size, right? Once again, I have the size of NFFT as 1024, but the size number of subcarriers that we are using is only 612. Then we'll have some null subcarriers, right? So how to, like, from 1024, how to select which number of, at which places my subcarriers will go, correct? So for that, what we do, we the standard, I don't standard says that, you can see from section 5.3.1, standard says that place this number, all the subcarriers that you have at the center. Okay, that's why now we need to calculate the first subcarrier where we need to place our 612. I think it will be clear in some time. I have some examples also. So like I have written, first subcarrier is chosen such that the empty indices are equally divided before and after the data indices. For example, I have 10 indices, okay, and I have, suppose I have NFFT size as 16, and I have data carrier as 8 only. So what I will do is I'll place this 8 in between 1 to 16. So top 8, top 4, and last 4 I'll put as 0, and from 5th to 12th I'll put the data, and 13 to 16 I'll put it once again 0. Clear? Once again, sorry. Suppose for example I have an NFFT size as 16 and K as 8. Right? How to place that? Should I place 1 to 8 as and rest all as 0? No, that is not preferred. We put 4 0 at the top, then 8 subcarriers, and then 4 0 at the bottom. Similarly, here we are going to do is in total 1024, the total 1024 subcarriers that is available. Okay, we just have 612 subcarriers. We'll place 612 at the middle, and some at the top, and the sum at the below will be 0 indices. Okay, so first symbol, based on that I have calculated, I've got the first index that we need to place is 207. So what you'll see is 206 at the top, 206 at the bottom will be 0. Okay, and from 207 to some maybe 818 will be the indices where all the subcarriers will be placed. Okay. Hope this is clear to you. And that's why based on that I'm calculating the first subcarrier, and based on the first subcarrier I'm calculating null indices. When you see the null indices is nothing but 1 is to first subcarrier minus 1. So 1 is to 207 minus 1, which will lead to 1 is to 206. Fine. So we have 1 is to 206 as the null subcarrier. Similarly, first subcarrier plus k. So first 207 plus 612 means 619 is to 1024. So sorry, 819. 612 plus 207 is 819 to 1024 will be null indices. Fine. Now what we are doing is, and then we have placed also. And here what would happen, null indices we know what is the CP length, what is the FT, what is the grid. I've just placed based on that. This function is doing that. Okay, now when we are moving ahead, if you see what we are having, this is a X is nothing but my data. Okay, that grid 612 cross 14 cross 18. This FT is we know, which is the CP length also we know. Based on this, what we are doing is we are just, and see, I'm giving an example also. This is the data index, right? We just calculated where we have put our data from 207 till 818. I'll give you an example also. From 207 to 818, we have the data. Rest all indices are 0. Right? This is a string which contains all the information of this one. What is the number of symbols per slot? What is the number of transmit antenna, IFT length? This structure contains that. Now, when we move further, we have the complete full grid whose size is 1024 cross 14 cross 8. Right? The data was having a size of 612 cross 14 cross 8, but now I filled this in my full grid of size 1024 cross 14 cross 8. Fine, this is clear. Now this is the full data that I have, which includes all the subcarriers. Okay, like this. Yeah. So if you see, the above ones are all 0. I'm not shown complete. The above ones are all 0, and this is the data where we have kept this from 207 to 234, and if I'm not shown this, below 206 samples will also be 0. Now we are going to the IFT. So this till here, this is now data. Okay, just now remember. So all the processing you see, I'll show you. Till here, what I've done is this part. If you go till here, I've done only this part. I've done till now. Okay, to all the information. Now we are going to do this. This will be easy. This you guys would have done earlier also if you have worked on OFDM. Now whatever data I have based on the sampling rate, based on the subcarrier spacing, based on the IFFT size, based on the numerology, based on how many number of slots are there, based on the CP length, we got till here. Okay. Now we are going to do the IFT and then insert CP. This is the simple parallel to serial. Then we are going to insert the CP that we are going to see. Okay.
Sir, I just want to ask one question.
Yeah, please. Yeah,
Uh,
please.
जो भी आप ये इसमें जैसे प्रोग्रामिंग में आप दिखा रहे हैं ग्रिड और ओएफडीएम मॉड्यूलेशन एंड ऑल, तो वो
Yes.
डायरेक्ट आप सिंटेक्स यूज कर रहे हैं या उसके बैकएंड पे भी आपने उसके लिए प्रोग्राम बनाया है?
Program, everything is there. We have to use program for everything.
आईटी टूल बॉक्स का डायरेक्ट सिंटेक्स आप कोई यूज नहीं कर रहे हैं मॉड्यूलेशन या उसके
No, no. That's why I'm saying I'm using for you guys something the code that is available by MATLAB. In the initial stage, I showed you right one MATLAB code, complete MATLAB.
या
So this is by MATLAB. So
और
you don't have to worry. But this MATLAB code in itself is of maybe 10,000 lines.
या सर क्योंकि
Okay.
मैंने एक टूल
So
बॉक्स देखा थोड़ा सा तो मुझे थोड़ा वो हुआ इसलिए.
correct. So that is of more than 10,000 of lines. So I've taken the bits and pieces from there. Okay, to explain, because understanding this complete MATLAB code is in itself too much difficult task. Okay,
So
and
आपने ये बनाया इसके basically considering only NR standard defined in this standard you have mentioned in your code also.
correct,
That's you have mentioned in your code.
correct, and that too only focusing on OFDM.
Only focusing on. Okay.
At the end, I'll show how if the time is there, I'll also show how I've taken those data from this main MATLAB example.
Okay. Thank you.
Mostly will be I'll show that we have time. So this is what we have in full grid that we got. Okay. Now when we are doing IFT, like I said, we are just doing the IFT, whatever information we had, and then we are adding the CP. This is the part where we are adding CP. It's looking complicated, but when you go into detail, we'll understand. Because why this is looking slightly complicated? Because of the fact that we had our CP length as different for different, right? 88 and then 72, 72, 72 like that. To make sure that is we are doing that way, we have taken that. Sometimes MATLAB write it in a difficult way, but you can do it in a slightly simpler way also. So this is a simple form thing that is happening. Once we have got this information, like I said, it's nothing difficult to do. Just take the data to the IFT and the CP. Data, IFT, and do the CP. And we have got the final output. And this is the modulation part. This is the transmitter part we have done. OFDM modulation is complete. Okay. Now we are going to the receiver part. And when we go in the receiver part, not much is there. In the receiver part, if I just showed you this diagram, the opposite will happen. First, we'll have the OFDM, whatever we are receiving over the here, Hx plus n. We need to do the demodulation. Here it is modulation part, then OFDM demodulation, and all this reverse operation will happen at the receiver side. Okay. Now, if I see, yeah, so we were here. You see here what is like we got the OFDM demod. This signal. This is the receive waveform I'm talking about. Hx plus n that we have got when it is passed to the channel. Okay. Now based on the received signal, I've taken a received signal. I'm not like I said, I'm not focusing on the channel part as of now. So I am assuming that I've got the received signal. Now based on the carrier information that I have, okay, all this information, like I said, the user, the receiver already knows what was the size of grid chosen, what was the subcarrier spacing, what was the symbol per slot, and all those stuff. Based on this, I'll be now demodulating my received signal using OFDM. Fine. So this is the received signal that we have received. Is this of size this cross 2? This cross 2 denotes the number of receive antennas. So this number of receive antennas here is 2. Okay. So number of receive antenna that we got is nothing but 2. Fine. Now we have got all this thing. This is fine. Now this is what we are going to calculate based on the number of now this is number of subcarriers. We got k. Okay, and this we can calculate. Now, like I said, we know the size grid. We know all those stuff. So this is what we got k. K is 51 into 2. Well, this is 612. Then once again we are calculating what to should be at the receiver. We have to calculate this few things that the transmitter will not transmit. That we have to once again calculate. Like for example, what was the first subcarrier? What is the null indices? Right. The first subcarrier was 207. What is the null indices? Like I'm telling you 600 indices in between 0 to 2, 1024, and all others are null indices. That is from 1 to 206 and 819 and 2102. That we have calculated in the transmitter also. Right. This is something symbol offset is removed from starting, and this I will explain in the next slide. This you'll get here. So I think it is fine to skip that now. Now, this all information why I'm repeating and not discussing details because we have already done it. K first subcarrier we have calculated, null indices we have calculated. The offset is, for example, like the same thing. If you guys remember, we had that symbol phases right at the transmitter. I said there it was phase pre-compensation. Now we are doing phase decompensation. And based on this section 5.4, they have given a formula. Earlier it was equal plus j. Now we have equal minus j. Okay, same thing we have calculated here also, like P, CP length plus info and FFT. There also, if you guys remember, right, we were doing CP length plus NFT. Similar way here also it has been done, and we got the symbol phase. And I've skipped a few lines in between where we are calculating symbol phase. So we got the symbol phase, and we are getting the final grid after doing this phase decomposition. Okay, what will happen? Like we know because it's a receiver, not much things have to be done. Once the phase decomposition is done, we have the data. Now we'll do first removal of CP. Right at the receiver, what happens? At the transmitter, we do first IFT, then at CP. At the receiver, first we remove the CP and then do the FFT. Same thing is happening. First, I'm removing the CP. Right. So this is the part where we are removing the CP. And see, you can see this is the actual one 1024 cross 14 with CP once. Okay, sorry. So this is the actual X we have. This is the X1, and after removing CP, we are getting this. Okay, so this is the actual one. After removing CP, we are getting this. So I can see that You just, if you are able to see this line, till 88, we have added CP at 88 CPs we have added, right? Prefix. So this is 88 sample if you see. If I'm removing all the 88 sample, what should be the first sample then? This one. Can you see on this part? We have this, right? 0.0755 plus 0.00619. This one is 0.0755. Okay, so this is the first sample that we have as the 88. Then second one is 0.0531, 0.05. So this clearly shows that we have removed the CP that we have added. Fine. Like I said, first value of post CP removal is nothing but the 89th value of the input. So this shows that CP is removed. What is the next process? The next process is nothing but FFT operation. So this is the FFT operation that we have. FFT operation. Once we have removed the CP, cyclic prefix, we are doing the FFT and we are done. Okay. Now we are done with the OFDM, like what I wanted to show. One thing I said, like I'll tell you in the end. Okay, what is happening? Like let us see, like just a basic. This is I'm just talking about the basic OFDM concept, important concept. We have this total length of 1024, where what we do in the basic concept of OFDM, last 88 sample, because we choose 88 number of the length of cyclic prefix at 88. Last 88 will be appended at the starting, right? Last 88 I'm choosing and I'm appending at the beginning. So overall, I said 1024 plus 88 which I'll append will lead to 1112, right? 1112. So this is the data after cyclic prefix is added. The same thing, we have this OFDM symbol 1 and OFDM symbol 2, right? Because here we were adding the cyclic prefix of length 88. For the second OFDM symbol, we added 72. So finally, we have this kind of thing that is being transmitted at the transmitter. I just wanted to give you a picture. This is at the transmitter. Now, when we receive it, what is there? When we are receiving it, we have this 121112, this, right? And this same thing. But now important concept will come here. What is happening? Suppose I want to detect only a part. I'm going to ignore the CP, right? How should we ignore CP? Now that is a question. Should I ignore? What should be the more practical way? Although the code has done in a slightly different way, but what should be more? Should we remove it from complete here, or should we remove it from here? How to remove? Which part should we remove? Okay. So what we can do is because we know the symbol interference will be there. So there is a high possibility that this will interfere with here. So this part of the code, this part, if you see whether I'm taking from this to this, there is a high possibility there will be overlap and there may be corrupted, right? So and similarly it will happen here also and here also. So instead of reducing the complete cyclic prefix from one side, okay, what we can do is just remove half part from here and half part from here, because we have done this 1 2 1 2 kind of thing. So I'm just dividing it into, suppose it's 88, 44 sample here, 44 sample here. So this 44 sample is here, right? Sorry, this is 1 2 here, right? Because if it is 1 to 88, here also 1 to 88. So 1 to 44 is here, so 1 to 44 is here. So this is 1 to 44, 1 to 44, 45 to 88, 45 to 88. So what I'm doing is I'm removing a 45 to 88 from here and 1 to 44 from here. Till I'm handling the complete data. And then what I will do is, you can see 45 to 88 I have here, and here I will have 1 to 44. And what I'm doing is I'm just taking this sample and so I once again got my original symbol. But in this way, what I'm doing is, if I'm instead of just removing this part or just removing the first part of complete cyclic prefix, there's a high possibility that this part also would be corrupted because of the inter-symbol interference between the two symbols, right? This is clear. So this is a good way. Instead of removing that completely, we are removing the half part here, then we are left with this, then we are moving this back to here. So this we have moved back to here, and we got this 45 to it. And this is the original symbol that we got without. So this is clear to everyone? Okay.
Yes, sir, it is.
Now let us go to the code, main code, like someone was asking also. So if you see, this is the code that is available in MATLAB. So just go to, I can help you also with this. We have enough time now. If you see, you just write MATLAB IFT PDSCH throughput. You can see you got a code. Okay. Like the chain that I was talking about, all those chains are there. Same code is there. Yeah, whatever I have, this see all the code is there. You can see the big code. Now let us go into the code detail. Okay. I will just try to focus on what we have done. If you see, before going to this code, what I'll show is the code that I have. Okay, you see whatever code I showed you, I've taken from that main code only. I'll just run it for you guys one by one, whatever we discussed now. If you see, this was that I said I will take a MATLAB code. I'll take the data from the MATLAB. I've taken the data before the OFDM block. So this is the before the OFDM block, 6.2 cross 14 cross 8 we had, right? Then this is the carrier information that I got. All those things. Suppose here subcarrier spacing I've taken it as to 15. In the PPT I was taking it to be 30, right? So here it is 15. Based on that, you can see the slots per frame change. Symbols per slot is 14. That is same always. But slots per frame for 30 subcarrier spacing was 2, and here it is 1. Because remember it was 2 for mu, right? Of numerology. Then this is size of grid 51. Right, this size of grid I've taken to be 51. And now what I'm doing is I'm changing the subcarrier spacing to 30 only, such that whatever we have discussed in the code. So 30, 51, everything is there. Now we can see the number of slots per subframe is 2. Okay. Now this is like number of transmit antenna I've taken to be 8. Center carrier frequency I've taken for time being 0. And all these things we were calculating, right? What is the mu, what is the number of subcarriers, same thing I'm showing you here, the main code. And this is, and then we had this subcarrier sampling rate that we calculated n into delta f. This is also the same code was there to calculate the extended cyclic prefix. Based on whether if it is extended, we'll get L equal to 12, else we are getting 14. So in this case, we are using normal cyclic prefix, that's why we are getting 14. You see, it was normal, right? Cyclic prefix mentioned is normal. That's why we are getting this as L equal to 14, not 12. And then we have got this slots per subframe. We have once again based on this, we'll get whether 512 or 144. Because we are using normal cyclic prefix, not extended one, we'll get NCPS 144. And then we are doing this finally. Based on that, we will have our CP length as 88 and 72. Correct. And then we are doing this phase compensation here. And then we are multiplying it, and then we are calculating the first subcarriers here, which we got as 207. Same thing what I have shown in the MATLAB code. I'm just showing through by after running this. Okay, we have calculated the full grid because here it was 612. We have got it 1024 based on the null indices that we calculated. Right. This. Now.
Sir, your slide is not moving. It is on that demodulation slide of cyclic prefix and OFDM symbol.
Acha, you're there. You're not in my MATLAB code.
Actually,
you're
it is
seeing
presenting that particular part, or you have to.
No. You are able to see my MATLAB, or you are seeing my PPT.
PPT, sir. It is visible. PPT in the screen. Na?
Okay. I was showing something else actually.
So kindly share your entire screen for MATLAB.
Yeah, I will do that. Can you see now?
Yes, sir.
MATLAB?
Yes.
So, okay, so I was showing this actually, whatever we have discussed in the, for example, in the PPT, I was just showing through this MATLAB code. Like we took this size it as 51 and all those stuff. So I'll go for the number of antenna 8 and all the code that I've discussed in the PPT. It is, I'm just running it once so that you can see the null indices that we got, the first indices that we got 207, and null indices that I was talking, right? It is from 1 to 206. Then we have put the grid which was of size 612 into full grid of size 1024. Then we did the FFT and all those things. So, and this year we have done the CP addition. Similarly, at the demodulation side, same thing we had, and we are doing all this stuff. Okay, whatever we discussed in the slide. The same thing I have written in the code. This is the code form. And finally, we got the demodulated signal, OFDM demodulated. This is from the code. But now let me go towards the main. Like as I said, from the MATLAB, if you go here, you can, the MATLAB, if you write the simple MATLAB 5G NR PDSCH throughput, this link will get opened up. The first link that is showing up, this one. Now you are able to see my tab, right?
Sir, it is MATLAB screen.
There's some
At
delay. Why
what
that is
screen
some...
you are sharing new radio PDSCH throughput?
Yeah, that only. Yeah.
There.
So you can see here, and now I will go through this code, this big code that MATLAB has written. You can see, right? I'll just open my MATLAB. This that code. Okay, I'll directly jump to the whatever we have discussed. Suppose, for example, you guys want to write your own code of this OFDM, how you have to approach that. I'll try to tell you. If you directly go there, first block of OFDM is here, and our OFDM info. Okay, if I go inside this, step in. Okay, there are multiple. They do validate input check, so we can ignore this. Then we go here. Then we go into OFDM info. Okay, then we go into OFDM info. There, if you do the checking, whatever I was talking in the about in the PPT, it is given inside OFDM info, where we calculate the numerology based on the subcarrier spacing, number of subcarriers based on the resource grid size, and few other things. Okay, so you can see this. All these things are there. And then finally the sampling rate will calculate it, and then the what is the length of OFDM symbols 14 based on the extended cycle prefix. Now all these informations are kept here. And this here it is only about doing initial calculation of this. Okay, there's so many other things that is not of use. If you are not interested in doing the windowing, that I have ignored now. So all these things are there based on windowing. What is the windowing technique we are using? So many, and like I said, they've done a very generalized code. Okay, we don't require everything. Whatever we require, I've shown in the PPT. But then we have to know also whether which is required, which is important, which is just an add-on. So here I said all these below things were add-on. We don't need them. Now further moving back, step out. We come step out. We did completed this part. Now further when we do the step out, we came back. So from here info, like I said in the PPT, they are calculating what is the number of subcarriers, what like based on the resource grid, what is the number of subcarriers, what is the size of FFT we are choosing. We are choosing like for example, we chose 1024. What is the size of CP that we have got, and all those things. Like for example, we gave this as input from your input. We gave this as input where we had subcarrier spacing, size grid, and all the stuff. And we are getting this output where we calculated this cyclic prefix length, symbol faces, which is here all zeros, sampling rate, FFT size here 4096, and other things. Okay, so this was calculated based on this information that is given in the carrier. Fine. Now we are moving ahead. These all things are not required for now. Now we need to look into where is the OFDM mod, where the OFDM modulation will happen, right? So this is all transmission happening, other blocks. Okay, yeah, we got. Let me search for where is the OFDM mod. Like I said, it's a big code and it's very difficult to get all the information from there. This we got OFDM modulator. After that, like I said, I took that on the right carrier and PDSCH grid. Once we have this grid and the carrier information, we need to go into this OFDM modulation. I'll run till here. Let me go outside this. Yeah, we came here. Now we'll get into this function. We go into this function also, there are so many things. We are validating input. We have OFDM modulate. We have OFDM mod. So we are interested in this part this time. Continue. Then we got into this. Now all those information that all the lines that I did, right? Based on the information symbol places, we are doing this phase pre-compensation that is being done here, and we are calculating first subcarrier, nulls and carriers, and based on that, we are doing the OFDM mod. So once again, this OFDM mod is important. Then when we are doing the OFDM mod, we are based on the transmit antenna and all those things, right? We are doing the modulation. So what I'm showing is how much complicated this is. You can see, right? Not that trivial. Yeah. Then we went here inside, and from here we did the IFT, and then we had the CP. So this is the complete transmitter that is there in the MATLAB code that we need to understand. So I've taken the parts which were important and kept it in one place and then tried to explain it. Otherwise, it would have been very difficult if I would have wanted to explain you everything without the knowledge of actual standard for all the other blocks, because this is covering the complete 5G standard rounding PDSCH. Like I said, right, there were four: PDSCH, PUSCH for uplink, PD is for downlink. Similarly, there is two for control: PUCCH, physical uplink control channel, and PDCCCH, physical downlink control channel. So there are four. This is one of them, PDSCH. With everything here, like you see, I'll just give you what all things are there. Like HARC, most important thing is hybrid ARQ. Suppose I'm transmitting something, you are receiving, but you have not received it correctly, so you'll send me a NAC, right? Negative acknowledgement. But if you're receiving properly, you'll send me ACK, positive acknowledgement. So all those things are also covered in this code. Okay, the channel estimation part. For example, before the data that can be transmitted, some channel has to be estimated. So channel estimation happening, synchronization happening. Yeah.
This is basically a total 5G implementation program. We have to select our part if we want to work on particular part of it.
Correct. Because it is very difficult if suppose someone wants to start to understand everything in detail. So but this is also difficult, I would say, without the understanding of standard, to take a part which you think, okay, this is important for me, or this is what we should do, right? For that, we need to first understand one part of standard. For example, OFDM, if you're interested, understand the standard content of OFDM, right? Okay, like I said, all this. If you are more interested, you can just go to the OFDM modulate. I've
This
given
standard
the
this
references.
program is available at one place in OFT in MATLAB, or it
Yeah,
is
this is one place only, right? This program is available at one place.
okay. This whole program is
Okay.
available at one, and it is
If
in
you go this,
2020.
yes,
Version 2020, I think. Release of 2020 of MATLAB.
2020 it was there, yeah. I'm using 2021, but yeah, 2020 also.
Sir, could you please share this particular link of MATLAB so that
Yeah,
it's
absolutely.
easy for us to find out?
Yes, yes. The chat I'm done.
Yeah, yeah. Thank you so much.
Right. And similarly, there is for receiver also. This was for the modulation. Similarly, if you go in there, you will have it for receiver also. The same thing. Anything else you guys want? Then I can tell you. Else we'll close otherwise.
So,
Because I'm done from my side.
okay. Any question from any of the participants? Any query from any of you who is working? Actually, sir, this topic is little new for everybody. They must be
Yeah, I
starting
understand.
this topic to have research on this particular part. So one of the participant was actually doing his PhD already in 5G. I think antenna design he was doing, so he was interested in listening all these things, basically.
Right.
Otherwise, it is new for everybody, basically.
Correct. It will be new for everyone. But yeah, that's always a time because these are standard thing in India. Nobody works. Very
Yeah,
rarely, like maybe 0.1% of people would be interested in standard. But this should work. Otherwise, because of this only, our country is lacking. I will just give you an example. What happens whenever, suppose, for example, 6G will come and 5G, for example, it came. So, because none of us were interested in doing any kind of standard related work, so all the prototypes, all the this IPs that were created, they were by foreign institutes or, for example, foreign industries. So all the money is going to them. Suppose if that their IP is implemented in the 5G, so they will get the revenue, right? So
yeah,
for every phone call, they are getting revenue, and because of that, their economy is growing, and we are just using it. We are their customer, and we are not getting any money. But in case if suppose around 6G, if we start working on this standard kind of thing, and in 6G, if we have our own IP, we send our IP to them, they select it, then the revenue will come to us, to our country. In that way, our economy will also grow, and the jobs also will be created. So this is one area where I think India is lacking a lot. And I think our government is now acting positively here with so many projects there on standard related things.
standard.
TSDSI is there. So there is one body is at TSDSI. If you guys are interested, you can go and search in website, Google, just TSDSI, right in the. This is based on, this is just Indian based standard body. This very, and this
Yes.
is
Okay.
TSDSI. So there you'll get all the information about what all activities uh,
So,
in
otherwise,
India is happening.
otherwise, we can just go for 3GPP standard references provided by
That
them.
is very difficult. That is very, if for a person who wants to start, this is very difficult to understand a standard document. That is very difficult. The language in which it is written, according to me, it's just because they want nobody should understand.
Yeah, maybe
So
because
very
I
difficult.
started release 15 for this frequency bands
Yeah.
information and all, but after some time I'll just shift it to an ITU and other websites so that I'll get it.
Yeah, so IEEE standards are very easy to understand, and it's like okay, like a paper, but 3GPP standard, the way they write is very difficult to understand. So we, when we started, we struggled a lot. Now we have, but yeah, still that is not an easy. I've read IEEE standard also 802.1, and they're very easy. They're written so nicely, so properly, like. But with 3GPP body, that standard they have written very. Don't know why they do it, but I always think that maybe they are doing intentionally so that not many people are there in that long.
Yeah.
So many steps are there.
So this body will have this TSDSI will have all these information regarding this 5G or
TSDS, TSDSI is a body, Indian body,
Indian.
telecommunication standard for India. So they are focusing on this only. Like I was giving you an example, right? What happens when the 3GPP sits? All the people are there from the developed countries and outside. Their requirement is very different. Like I said, like their requirement is 500 kmph, kilometer per hour kind of set. We
Okay.
as in India, we don't want. As of now, we just want our rural cities, rural areas to be connected. Our requirement is not 500 kmph. So this body is there, which is talking about our requirement as an India people requirement.
Okay.
We do some kind of patenting there and do some kind of work, and then send it to 3GPP saying no, we want this also in your standard. Maybe in 5G later releases 17, 18, 17 is anyway came 18, 19, 20, whatever, so that our requirement is fulfilled. Otherwise, what we are doing is we are buying their phone, we are buying everything, but our requirement is not fulfilled.
No. We are
Most of the
just
requirement that is fulfilled by for the developed
implementing
countries.
the standards they are providing us. They are
Correct, correct. So that's why. So now what these people are doing is this is very new initiative. So in few years maybe our requirement will go into 3GPP in this releases, and then we'll get much and better benefits. And maybe if we are doing our own IPs are going to standard and when we are using it, so our country will benefit in that. The revenue will come to here, not to some other developed country. So that is the idea. And all institutes are part of this as of now. All the IITs. When I joined, Roorkee was not a part of it, but now we are processing that Roorkee also to be a part of it. Other IITs are there. All companies are there. All telecom companies are there in that. That is good. Anyone can go and visit. And so many talks keep on happening every week or twice a week. One talk happens there, which is good for people to attend.
yes. So thank you so much, sir, for such an informative session. And it is basically difficult to give this type of information in online modes. Basically, I there is a lots of struggle.
No, this kind of information, not only online, offline, it's very difficult because the audience does not have any information about it.
Yeah. It's because
So
there
for
are
them also,
uh, some struggle to understand the MATLAB coding and all that.
that will happen.
Thank you so much, sir, for your informative
Yeah.
session. And thank you all the participants. If any query from any of the participants, they can ask. Otherwise, we can call off the session.